Today I'll be talking about our work on quantum correctness by construction. This is joint work with Ina and Michael. I think this is something that we can all agree on, that the larger programs get, they often contain mistakes and bugs that we need to catch. And for over the last 6 or so decades, there have been many approaches to verifying these programs. Some based on logic, like Hoare logic and incorrectness logic, and model checking, analysis, testing, and so on. But interestingly, quantum algorithms present new challenges. The first, maybe more immediate one, is that we don't have enough hardware, so you can't do things like just run and test your program. And even if you could, you can't use standard debugging techniques like inspect the program state as you run, because measurements collapse the state and they disrupt the computation. So it's all the more important to be able to have formal methods to verify quantum programs. So we build our approach on a standard logic called Hoare logic to verifying programs. To recap, Hoare logic is you state program correctness as a Hoare triple, which is a precondition, a program, and a postcondition. And this Hoare triple is said to be valid if for every input that satisfies the precondition and you run the program, it has to, the output state has to satisfy the postcondition. And there are two methodologies of using Hoare logic to verify programs. The standard one, which was where it started by Tony Hoare, is called post-hoc verification, where you take a program, you use the logic, you phrase the correctness constraints as these triples, and you build up a proof for the program. So this is a bottom-up approach where you take the entire program and you try to prove that it's correct. And there is another approach which we can use to also verify programs, which is called correct by construction or refinement programming, where you instead start with the specification of what you want your program to do, and you incrementally refine the program, build it step by step, while ensuring that each step that you do maintains the validity of the program. And this is like the opposite. This is a top-down approach where you can discover details on the fly, and this is somehow more closer to how one would actually discover an algorithm or build something, as opposed to being given a program to verify. So first, this standard logic has been extended to quantum logic, like for quantum Hoare logic, where we model our the pre and post conditions as quantum predicates, which are POVM elements, and the degree to which an element holds is given by the probability that if you measure the state with this POVM element, like the outcome, the probability that you get this outcome. And this is similar to how it's modeled in probabilistic logic. We also assume standard denotational semantics on quantum programs that map mixed states to mixed states, and these are in general arbitrary, like completely positive trace non-increasing maps that correspond to physically realizable quantum operations. And the correctness of a quantum Hoare triple, stated the same way, says intuitively says that the probability that the precondition holds on the input state is at most the probability that the postcondition holds on the output state. And intuitively, this just says that things that were correct continue to remain correct, and I mean, you could have accidentally also made other things correct as you run the program. So we build our framework on a very standard programming language called the quantum while language, which is a basic statement-based instruction language with support for conditionals and unbounded loops based on classical measurement outcomes. That is, you measure some quantum register with a binary outcome, and depending on the classical measurement value, you decide whether to continue the loop or enter the branch. So we extend this with a whole which has a pre and post condition tag to it, and this is in principle the same way it is done for refinement programming with typed holes, where you tag a blank program with a type, and here we tag it with a pre and post condition. And what we want to do is, at the end, when you construct a program starting from a hole, you want the corresponding Hoare triple that you get to be valid. So how do we do this? We give a set of refinement rules that one can use to incrementally fill in the program. A refinement rule is of the form, you start with the whole and you can go into some other program S, possibly containing more blanks, when a certain set of conditions for it are satisfied. And the advantage of thinking this way is that once you perform a refinement and you know that it's correct, you can then forget the conditions that you've already checked and just focus on each independent, like each hole that you have in the remaining program independently without worrying about the structure of the program. I'll give a few examples of basic refinement rules that you can use. So each refinement rule comes accompanied with some particular condition that you would have to check. Either you check it immediately or you existentially quantify and then look at it later. So a simple example is if you initialize a quantum variable q to, let's say, the 0 state, then you have to check this corresponding matrix constraint. Similarly, if you apply unitary, you'll have a constraint that says P implies U dagger QU. We can also just refine to a sequence of 2 steps with an arbitrary intermediate condition of choice. And maybe the more interesting rules are first bounded loops. If you want to repeat, if you want to refine to a repeat statement that repeats n times, the body has to satisfy a family of constraints where Rj is the property that's true after the jth iteration, and then after running the loop body once, like you basically make one step. And this, we can extend the same to unbounded loops that says that if you refine an arbitrary hole P blank Q by running a measurement B on a quantum register Q, both picked by the person like building the program, then you'll get a similar family of holes that where you have these series of predicates R0, R1, so on with some particular limit R. And intuitively, this hole captures that the assertion Rn captures the fact that the state will run in the loop for at most n iterations. So the condition for the hole says that if you start with a state that would quit after n plus 1 iterations and run the body, and then after performing the measurement, either you get the outcome 0 and then it satisfies the post condition because you've exited the loop, or you get the measurement outcome 1, that's B1, and then it satisfies Rn, that is, it would only continue for n more iterations. So we show that our refinement system that we give is both sound and complete, that is, any constructed program is correct, and we can also construct any valid program that can be proven in the corresponding Hoare logic using using some sequence of refinement rules. We show a few examples in the paper to capture standard patterns that people can find useful to build larger programs. One common example is the repeat until success pattern, which is used, for example, in magic state distillation and so on. So this is one possible refinement rule that you can use to get the repeat until success pattern, which is the I here is the identity operator, which says any state. So the hole you have says, starting with any state, I want an output that satisfies Q. Then you can refine it to a loop that says you keep measuring the variable Q with the orthogonal complement of this predicate Q. And you have 2 requirements that you need to satisfy. The first one says that if you start in the orthogonal complement of Q, then with probability epsilon, you will end up with a state that satisfies Q that says each loop iteration works with probability epsilon. And this is something that you can pick while refining the program. And the second one effectively states that the program terminates, that is, you start with something in the orthogonal complement of Q, and you'll end up with a program that terminates, which basically says that the loop body terminates, preventing the loop from diverging. We also show a few more constructions for Grovers and QFT in the paper, which I will have to omit for lack of time. So we basically built a starting step towards bringing ideas from refinement programming to verifying quantum programs. But there are naturally more things that we like to look at. One is use more expressive languages like we've seen in the talks before, and also capture more high-level patterns. Repeat until success is a nice pattern, but it would be nice to have amplitude amplification as a first-order pattern in the language, in the refinement calculus, and also use other calculi to maybe say build efficient programs by construction using an expected runtime calculus, for example. And will also be nice to look at ways to use concrete assertion language to efficiently represent these predicates and then mechanize checking these conditions using like libraries that are capable of doing it in Coq and so on. So to summarize, we give like a framework to use refinement programming to build correct quantum programs, like programs that are correct by construction, and you can use this to refine to large programs and focus on one part at a time. And as you through the refinement process, it helps you focus on each subpart of the program, and you can decide on the choices that you have to make along the way, and you can easily extend it by adding new like refinement rules based on the ones that we already have. Yeah, thank you for listening.
Very good. So I just want to comment on your future work there. I think if you could do oblivious amplitude amplification, that would be very cool. So the flavor of what you're doing has some synthesis to it, right? That you like to discover things as you go. How do you think of your work versus other papers we know that do synthesis without thinking about Hoare logic?
Without thinking about what?
Hoare logic.
I see. So I guess you can use this as one way to do synthesis. Like if there is like a synthesis-based tool that uses Hoare logic as its specification language, then it would be one way to automate maybe some easier parts of the program. Like larger parts of the algorithm are usually hard to synthesize just automatically.
Right.
But maybe smaller steps can be synthesized, yes. Yeah.
Do you run into some kind of scalability problems like other approaches to synthesis do sometimes?
No, so in this we've only given the theory, so we've not implemented it.
So that's future. Okay, so.
Hi, I'm Cesar from MPI SP. So did you have to define I suppose you had to define a Hoare triple for each of the operations of your language, right?
For the refinement rules, yes, that's correct. Yeah.
Okay, and did you look into to build like a weakest precondition calculus for this, or?
Yeah, so actually, if you look at the rules for the basic statements, these are effectively the weakest precondition rules. The right side term here is the weakest precondition of Q with respect to this program, and P is so you need to have P implies that, and of course for larger programs it's hard to get the weakest precondition.
Okay.
For more complex programs, but yeah, for basic statements, it is effectively the weakest precondition. Yeah.
Okay, thank you.
Other questions? Yeah. Very good, thank you.